This is the Chapter 10 Enzymes commentary. In this commentary, we're going to be talking about enzymes. So, in a nutshell, enzymes optimize the collision alignments of incoming substrates, which thereby lower the activation energy. So in this case right here, this is the uncatalyzed reaction. So if I have substance A and B, I'm going to need to provide this amount of energy in order to create our final AB product. Whereas with the catalyst present, it actually lowers the activation energy required. Let's go ahead and see an example of a catalyst in motion. So in this example right here, I have two types of substances, reactant A and B. I'm just going to go ahead and do the simulation without the catalyst. So in order for them to react, they need to collide against each other. So this is 101 chemistry collision theory. They need to hit each other with enough energy as well as optimally collide with each other at the right angle. So in this case, you can see how the reactants are being used up, forming the products, although it is still taking a while. Now I'm going to go ahead and add in catalysts. Catalysts are not used up during the reaction. Their only purpose is to speed up an existing natural reaction to begin with. So basically, the enzymes are scooping up reactants A and B and causing them to optimally align, as well as creating an environment which lowers the overall activation energy for that reaction. Consequently, already all of the reactants have been used up except for two, and this one's about to scoop up the other one if it can find it, and it's right over here, but will it be able to find it? Who knows? My point is this in that it again catalyzes or speeds up the reaction between A and B. These biological protein-based catalysts we call enzymes. Now, showing you a nice picture. If I can get the screen. There we go. So showing you a nice picture. Again, here is our protein catalyst. I'm going to go ahead and highlight the yellow area. This is what we call active site on the catalyst. So this is where our reactants A and B are scooped up, and the environment inside the active site is such that it catalyzes or speeds up the reaction. Keep in mind, all of these reactions could occur naturally on their own. It may take days, months, years for that reaction to occur, whereas a catalyst speeds it up into seconds or nanoseconds. So that is an enzyme. Instead of using the word reactants in biochemistry, because everything is catalyzed, instead of using the word reactants, we like to use the word substrates. Substrates. And these are the reactants that are going to be catalyzed inside the active site of the enzyme. There are different types of enzymes. We have enzymes which have absolute specificity. That means they only work on one type of substance. So for example, we have a urease, and its job is to break down urea into ammonia and carbon dioxide, but it only works on that one substance. So it's specific, absolutely. Relative is when an active site will allow a class of biomolecules. So for example, proteases are digestive enzymes which break down proteins, and they'll break down a variety of different proteins. So it's a relative specificity. Most enzymes are stereochemically specific. They only work on D or L chirocarbons. So for example, enzymes that catalyze sugars are stereospecific to D, whereas enzymes which break down, for example, proteins, such as proteases, they're stereospecific toward L isomers. Have the wrong isomer, then the isomer Have the wrong isomer, then the enzyme will ignore that particular substrate. As a point of reference, cells contain thousands of molecules that can react with each other, but due to enzymes present, they actually steer. They control the rates and amount of product, So therefore, the enzymes are used to regulate the desired biochemical products. Here's an example of again, enzyme, which is absolute toward this one specific type of substrate. Its name is urea amido hydrolase. Notice all enzyme names always end in the suffix ase, ACE. The rest of the enzyme name, if the biochemist decided to, is usually based on its function. So it was used to break down this. Notice it's got two amides on here, used to break down the urea molecule, and it's two amides with water into carbon dioxide and ammonia. So it's a urea amido hydrolase. So the ACE tells you that it's an enzyme. Here are the 5 classes. Know these. Oxidoreductases, they're responsible for catalyzing the transfer of electrons. We see this when we're replenishing our molecular batteries, ATP. Transferases is when we're designing new biomolecules and we need to transfer one functional group from to another. Hydrolases, we see these in digestive enzymes when we use water to break down, for example, proteins into amino acids when we digest it. Lyases, we use to add double bonds. Usually we use those when we're breaking down fats for energy. Isomerases is when we're rearranging the isomeric shape of that particular biomolecule. And ligases is usually when we build, for example, when we build monosaccharides to disaccharides, when we build, in general, biomolecules. Usually it requires extra energy, which we have ATP present for, and provides an extra charge or boost in order to get the reaction going. Know these classes of enzymes. Enzyme cofactors. These are any types of metal ions or any type of organic molecules. And these are used to go ahead and activate an enzyme. So here's one way that we can regulate enzymes. That's through enzyme cofactors. So if it's a metal ion, you might see it as zinc ion, for example, or iron ion, which you would find in hemoglobin in order to make hemoglobin active in transporting oxygen. If it's an organic molecule, oftentimes we refer to these cofactors as coenzymes. Most of these coenzymes we actually can only get from our diet. We can't make them. So if you have a poor diet, you may not be getting the proper coenzymes so that your enzymes are working properly. These cofactors can temporarily bind to an enzyme, making it active. On the other hand, it can leave the enzyme, making it inactive. So it's one way we can control it. Please do not confuse this with prosthetic groups, such as metalloproteins or lipoproteins, whereas prosthetic groups, those other biomolecules are permanently attached. If an enzyme is off, it's apo. If an enzyme is active, then we say it's a holo. So apo enzyme is for an enzyme that's off, holo enzyme is for it being active. In general, in order for this enzyme to be active, we need to add in our cofactor. The minute the cofactor is added into a special slot within the apo enzyme, it makes it active, in which case it will start catalyzing the substrates. So know this general reaction, know these terms, apo and holo enzymes. Here are examples of holo enzymes, and in red, those are its coenzymes, NADH, vitamin B, and then here's one where it's an inorganic ion, in this case zinc, in order for it to be completely active. Again, take them out, then they're inactive. Here's the overall reaction steps. Usually, in order for a reaction to occur within a specific amount of time, since they can all occur naturally, but what good is a reaction if it takes months to years for it to occur? We have the enzyme substrate. This is the complex. That's when they come together, and then the enzyme catalyzes the necessary reaction to form the product. The product is then freed, and an enzyme is recycled for another round. Enzymes are not destroyed during every catalyzed reaction. They're simply recycled for the new reaction it's going to catalyze. So I already talked about active sites and substrates. Let's move on. To summarize the active site and substrate process, most people think of this as a lock and key model, where the active site is the lock, the desired substrate is the key. And just as only one type of key can fit into a lock, only one type of substrate can fit into the enzyme. There are other substrates that may be present, but if they have the wrong shape, then they won't fit into the enzyme, therefore they will bounce off and not be catalyzed. Induced fit model goes one step further. And it makes a general assumption that when you have the desired substrate hit the active site, the overall shape of the enzyme will change, inducing a much better fit around the desired substrate, allowing for optimal catalysis to occur. So in this picture right here, we have before, it then fits in, and then the shape of the overall enzyme actually changes a bit such that it fits snugly around, the active site fits snugly around the desired substrate. So we call this the induced fit model. The minute the catalysis is complete, the substrate will then leave, and then the enzyme will retain its original shape along with its original starting active site shape, and then the cycle repeats. Sucrase is an example of a scissor enzyme which is used to snip apart disaccharides such as sucrose into monosaccharides. And when it fits into the active site, it snips the glycosidic linkage, breaking it up into disaccharides. Carbonic anhydrase is our most potent, our most powerful enzyme, and has the highest number of catalyzed substrates for any one molecule. Its purpose is to take carbon dioxide gas, which is released during the breakdown of sugar, and combine it with water to form carbonic acid. So that way it's dissolved in your blood plasma, or the liquid part of your blood, rather than forming gas bubbles, because gas bubbles are bad. So here we see it's zinc atom. This is the overall active site that's present. Food for thought, here are the different steps. This is the actual mechanism. I'm not testing you on the mechanism. Just know that carbonic anhydrase, and it contains the cofactor zinc along with its prosthetic group. This is just a prosthetic group. I take that back. It's not a in this instance it wouldn't act as a cofactor because it's permanent. So in this case, we see the mechanism for forming carbonic acid. Now, we need a way of telling people how potent or how much enzymes are present during enzyme activity. If we're taking a look at one single enzyme and we want to know how potent it is, then we look at its turnover number. And this is the rate of one enzyme, this is the rate of the number of substrate molecules which are turned over in a chemical reaction, or in a catalyzed chemical reaction per minute. So in summary, it's the potency of the enzyme. Carbonic anhydrase has the highest turnover number of any enzyme in the body. Turns over 36 million molecules of carbon dioxide of carbonic acid in 1 minute. So it's highly potent. Enzyme International Unit is the quantity of enzymes that catalyze the conversion of 1 micromole. So we like to use international units to measure how much enzyme is present, and this can actually be used when we're diagnosing diseases based or any type of ailments for enzyme concentration. Whereas turnover number looks at the individual characteristic of a particular type of enzyme and how potent it is. We have different factors for increasing or decreasing the reaction rate of enzymes. So one way to go ahead and increase the overall reaction rate is to increase the amount of enzymes. Another way is to go ahead and increase the amount of substrates. Notice for this other one right here, if I have 2 enzymes and I have a couple substrates, by increasing the amount of substrates, then yes, I can increase the amount of reaction rate. But what happens if I have a ton more substrates? Well, it turns out that although enzymes are pretty fast, then you start to get backlogged. And substrates kind of have to conceptually wait in line in order to use the enzymes. So there is an upper limit into how fast enzymes can turn over substrates, and once you reach the upper limit and they cannot work any faster because you have too much substrates, then you say the enzyme is saturated. So the maximum velocity, aka enzyme saturation, is the maximum rate that can occur if you have a limited amount of enzymes. So again, no matter how much I increase the substrates at that point, the enzyme catalyzed reactions will not go any faster because you just simply don't have enough enzymes. So you say the reaction rate is saturated. Let's move on. Temperature. This should be easy. Enzymes are proteins. So if you increase the temperature, then the protein, along with its desired active site, will denature. It will fall apart. Likewise, we talked about the induced fit model, where the protein needs to be flexible and fit around the substrate. Well, if the temperature is too cold, then for all intents and purposes, the enzyme freezes. So it cannot do the induced fit model. Substrates will come in and then leave. So there is an optimal temperature. Protein's shape. A protein's shape is dependent on a pH. By changing the pH, you change the characteristics of the side chains, and the protein can fall apart. That's why we need a blood pH of about 7.6, for example, so that way the hemoglobin proteins can work properly. Otherwise, they would fall apart, and then you'd lose all that precious oxygen. So you need an optimal pH in order to have a fully functional enzyme. So we'll go ahead and we'll stop here at this section.